Well, welcome back to part 2 of 11.6. We're going to start with the other two tests, ratio and root test. The ratio test is based on taking the limit of a sub n plus 1 over a sub n. So the top part is what we've done before when we're checking to see if it's decreasing. And these are going to be in absolute value bars for all three setups. And so if the limit of the first one is less than 1, then our series is absolutely convergent. If our limit is greater than 1, or the limit goes to infinity, then the series is divergent. And if our limit is equal to 1, then the ratio test is inconclusive, and we're done. There's nothing we can conclude. We're done. So this is very useful when the series that converge rapidly often factorials and exponentials. So looking at this example right here, you can have an exponential on the top, a factorial on the bottom. So starting with my ratio test, here for the n, I'm going to put in n plus 1 in that power. On the bottom is going to be n plus 1 factorial. Put the original on the bottom, but we don't divide by fractions, we multiply by its reciprocal. And then the next thing we want to do is we want to work on breaking these down so we can make them the same. So for example, up here, if I take out a negative 3, so negative 3 to the n times negative 3 to the first, now I can cancel the negative 3 to the n powers. My n plus 1 factorial, if I break that down to n plus 1 times n factorial, then I can cancel the n factorials. So I cancel that out, I'm left with the absolute value of negative 3, well that becomes just 3, over n plus 1, which is going to be positive anyhow because we're starting with n equals 1. And as well, we can see as n goes to infinity, this is going to get infinitely large, so this is 0. And that's less than 1, and based off of our ratio test for condition number 1, our series is going to converge absolutely. So on the test, you will write down the series, whatever it may be, converges absolutely by the ratio test. Okay? Next example. Oh, we got n's everywhere. N to the n power over n factorial. Time for the ratio test. Again, be careful. You got to put an n plus 1 in the power on the top, n plus 1 for the base, and n plus 1 for the factorial. Again, we divide by n to the n over n factorial. No, not really. Let's just write it as multiplying by its reciprocal right away. So we can start doing some breaking down. Let's take out an let's see, what should we break down first? An n plus 1 to the n power times n plus 1. And let's break down our factorial here. N plus 1 times n factorial. So we can cancel there. And we can cancel the n factorials. And now I'm stuck with n plus 1 to the n power over n to the n power. And since they both have the same power, we're going to rewrite this as just one fraction raised to that power. And then on the inside, I'm going to separate these as two fractions. N over n will equal 1. And 1 over n will stay the same. And this looks very familiar to me. You may have had a good college algebra teacher that demonstrated that this is the definition of your base e value. So here's that function right there, 1 plus 1 over x to the x power. It flattens out. It's approaching that red line, which is represented by base e. Well, e being 2.7 is greater than 1. That's step 2 of our ratio test. So our series diverges by the ratio test. All right, example 6. Oh, we got all kinds of stuff here. So ratio test, be careful here. You got to put an n plus 1 into the power on the n. The n plus 1 goes in here for the binomial, which makes that n plus 1, which is now n plus 2. And be very careful on this power because you got to write this as 2 times n plus 1 plus 1. Again, multiplying by the reciprocal of my original sequence function. So let's clean up that exponent right here. So that's 2n plus 2 plus 1, which is 2n plus 3. Now let's start breaking things down. For example, the 10 here. And 10 to the n times 10 to the first. Here on the 4, we want this to be 2n plus 1, so we got to take out a 4 squared, and then we'll have the same denominators there. So now we can start to do some canceling. Our 4 to the 2n plus 1 cancels with 4 to the 2n plus 1, 10 to the n, 10 to the n. And here we have our simplified fraction. Well, 4 squared is 16. 10 over 16 is going to be 5/8 multiplied to this fraction. But look at our fraction here. Our horizontal asymptote rule says that, oh, top power is 1, bottom power is 1. Your leading coefficient ratio is 1 over 1. So that fraction is approaching 1 as n goes to infinity. So 5/8 times 1 is just 5/8. And 5/8 is less than 1. So that's our ratio test, step 1, that says that this series converges absolutely by the ratio test. So we're going to make sure we rewrite this all out on the test. All right, time for the root test. Kind of the same setup, but now you're going to see the nth root of our sequence function in absolute value bars. 3 different levels again to test, but the same kind of inequalities. If the limit is less than 1, your series is absolutely convergent and therefore converges as well. If your limit is greater than 1 or equals infinity, our series diverges. If it's equal to 1, then our root test is inconclusive. We can't tell if it converges or diverges. So this again works great when you see things raised to the nth power only. All right, so let's determine whether the series are absolutely convergent, conditionally convergent, or divergent. Here's this fraction raised to the nth power. Hint, hint, root test. So we're going to take the limit as n approaches infinity of the nth root of the absolute value of our sequence function fraction, 5n plus 4 over 3n plus 7, all to the nth power. Well, again, the nth root and the power of n will cancel each other out. I also dropped the absolute value bars because these are going to be all positives here, because n starting at 1. And, well, wait a minute. Here's your horizontal asymptote test. N to the first, n to the first, powers are the same, leading coefficient ratio is 5/3, that's your limit. Well, 5/3 is greater than 1, so this series diverges by the root test, the second step of the root test. All right, next example 8, we're going to use our root test again, but notice here we have a power of 3n. We do not take it to the root of 3n. It's just the nth root. So this 3 as an exponent will stay part of your answer. All right, we don't change that root on the outside. It's always the nth root. So the limit as n approaches infinity, we have 3n plus 1 over 5n to the third plus 7, all raised to the third power. On the bottom, you can see top power 1, bottom power 3. So this is approaching 0. So whether I go to the third power, it's still going to approach 0. And 0 is less than 1, so this series converges absolutely by our root test. Okay, example 9, -2 to the n over n to the n. Let's rewrite this because they have both the same powers as absolute value of -2 over n all to the nth power. Taking the nth root of something to the nth power cancels out. Absolute value of -2 is 2. So now, well, wait a minute, this is a harmonic series, 1 over n. Okay, so this limit goes to 0, which is less than 1, so this series converges absolutely. Example 10. All right, we're going to use our root test again. The nth root of the absolute value of this fraction to the nth power cancels out. Our absolute, let's see, we have n squared plus 7 over n squared minus 4. So here it's going to be equal to 1. Your powers are the same, 1 over 1. So therefore this is inconclusive. We can't tell if it converges or diverges.